We're going to work on the first set of problems dealing with vectors, the first set of sample problems dealing with vectors. If you've noticed, if anyone is in a wheelchair or otherwise needs help getting into Martin, there's no wheelchair ramp going into Martin. There's a little lift by the side, but not a ramp. By regulation, to be ADA compliant, a wheelchair ramp cannot have an incline greater than 5%. And so if the steps in front of Martin Science Building on Randolph's campus are 1.5 meters tall, how far away would a ramp have to start at a minimum to avoid being too steep? If you imagine sort of a regular flight of stairs, if you put the base of the ramp right at the bottom of the stairs, that'd be a really steep ramp. So your ramp has to start further away to make it sort of viable to use as a wheelchair ramp. And we're going to pretend that the ground is flat in front of Martin Science Building. Those who know it well know that it isn't really, but we're going to pretend it is. So what's the question really saying? We could picture our steps here on the right and a potential ramp here sort of shown by this long line at a fairly shallow slope. That ramp is going to go from the ground here at 0 meters up to the top of these steps at 1.5 meters. We can picture that as basically a right triangle with a height of 1.5 meters, and this angle can't be anything greater than 5 degrees. If we want to figure out the shortest distance away that the steps can start, we want to figure out how far away this would be when that angle is 5 degrees. This distance here would be how far away we are from sort of the top of the steps, how far out that ramp would have to start. So taking that triangle that we just had and knowing that the tangent of an angle in a right triangle is equal to the length of the side opposite that angle over the length of the side adjacent to that angle, we know that in this case the tangent of 5 degrees would equal to 1.5 meters divided by x, the length or the distance away that the ramp would have to start. Doing a little bit of plugging and chugging, we see that x would be 17 meters. If you're kind of wondering what this has to do with vectors, what we really did was just sort of a version of resolving a vector or thinking about the x and y components of a displacement vector that we know would be length 17 meters in x and 1.5 meters in y. I do want to give you guys a word of caution when you're working with the inverse tangent. So I have two vectors shown here, vector A and vector B. If we resolve A into its components, A sub x is 1 meter and A sub y is 1.5 meters. If we resolve vector B into its components, B sub x is negative 1 meter and B sub y is negative 1.5 meters. Okay, so say we want to figure out the angle theta each of these would make with the positive x-axis. Remember we said you can figure out that angle by saying the tangent of theta equals to the y component divided by the x component. So in this case, tangent of theta equals 1.5 meters divided by 1 meter, or, well, tangent of theta equals negative 1.5 meters divided by 1 meter. If you look at this, you can tell that these values are going to have to be the same. 1.5 meters divided by 1 meter is going to equal to 1.5, and negative 1.5 meters divided by negative 1 meter is going to equal to 1.5. And if we number crunch, if we take the inverse tangent of both sides of those, we get that theta A is equal to 56 degrees. And that makes sense if we imagine a line parallel to the x-axis here. The angle between that line parallel to the positive x-axis and vector A is probably about 56 degrees. So that seems logical. If we do that with B, we also get 56 degrees. But the angle that B makes with the positive x-axis that we're going to measure goes all the way around here, 90 degrees, 180 degrees, and further. Why does that happen? Well, the tangent function is different from the sine or cosine function in that it repeats every 180 degrees. So this graph is a graph of the value of the tangent versus the angle. We have the angle in degrees or the angle in radians. And what we see is the values are only unique between -90 and +90. That means that for any number other that's sort of outside of -90 and +90 degrees, that value's already, sort of that value for the tangent is also represented in the range -90 to 90. Anytime you use inverse tangent on your calculator, it's going to give you an angle between -90 degrees and 90 degrees. It can't tell the difference between that angle that has a positive x and a positive y and one that has a negative x and a negative y. So if the x component of your vector is negative, you'll need to add 180 degrees to the answer that you get when you use inverse tangent. So if you had the angle that we just had, so we had negative x and negative y, and that gave us an angle of 56 degrees. We would need to add 180 degrees here, and we would see that our actual value would be 180 plus 56, or 236 degrees would be the real angle measured from the positive x-axis for vector B. Okay, now here's a problem that you're going to get to do some work on. So Jim, for some unknown reason, has decided to do some unusual calculations, and he is determined that he will get much better cell phone signal if he is 1 kilometer to the east from his current position. And he is desperate for a good cell phone signal. Unfortunately, the road does not go directly east, and Jim's really afraid of snakes, so he's not going to walk off the road. Jim is only going to follow the road, and he wants to go 1 kilometer to the east. The road is straight, and the road goes 10 kilometers north of east. So that's the direction of the road, is 10 degrees, sorry, not kilometers, 10 degrees north of east. We want to figure out how far Jim is going to have to go to be 1 kilometer east of his original position. So we have sort of northeast, south, and west drawn just like x and y coordinates. This vector indicates the direction of the road, so it is 10 degrees north of east. And we want to figure out how far along this vector Jim will have to go before he is 1 kilometer east. So which of the equations below relates the total distance Jim has walked along the road here to the distance traveled in the x direction? So we're going to make the total distance along this vector d, and the distance traveled d sub x. The distance traveled in the x direction would be d sub x. Using that equation, go ahead and determine the total distance d that Jim will need to travel so that d sub x equals 1 kilometer. So Jim was having some issues before, now it's Sue. The state line is 2 kilometers west of Sue's house. And, well, Sue's been causing a little bit of trouble lately, and she's being chased by state police officers. The state police officers cannot follow her across state lines. Yes, this is kind of a made-up problem, but try to make it at least a little bit interesting. So Sue's a little bit worried, though, that the police know this, and so if she runs due west, they're going to have an easier time following her and finding her because they're going to check directly along that path. So instead, she decides to run 20 degrees south of west. Sue runs for about 4 kilometers, and then she gets so tired she cannot run any further. She's absolutely exhausted. If she stops here, Could she still be arrested by the state police? Is she still in her home state, or has she made it 2 kilometers west and crossed the state line? We're going to take north to be positive y and east to be positive x, just like we did in the compass that we drew earlier. There we go. So we have the same coordinate system, and we want to figure out how far west has Sue traveled when she stops running after 4 kilometers. There's the path that Sue has taken, which is 20 degrees south of west, and she's run 4 kilometers along that path. Next question, could she still be arrested by the state police?